Balancing a car is controlling weight transfer using throttle, brakes, and steering. This video explains the physics of weight transfer. You will often hear coaches and drivers say that applying the brake shifts weight to the front of a car and can induce oversteer. Likewise, accelerating shifts weight to the rear, inducing understeer, and cornering shifts weight to the opposite side, unloading the inside tires. But why does weight shift during these maneuvers? How can weight shift when everything is in the car bolted in and strapped down? Briefly, the reason is that inertia acts through the center of gravity of the car, which is above the ground, but adhesive forces act at ground level through the tire contact patches. The effect of weight transfer are proportional to the height of the central gravity of the ground. A flatter car, one with a lower central gravity, handles better and quicker because weight transfer is not so drastic as it is in a higher car. The rest of this video explains how inertia and adhesive forces give rise to weight transfer.
A car in straight line motion at a constant speed will keep such motion acted on by an external force. The only reason a car in neutral will not coast forever is that friction and external force gradually slows the car down. Friction comes from the tires on the ground and the tendency of a car to keep moving the way it is moving it the inertia of the car, and this tendency is concentrated at the point.
When a force is applied to a car, the change in motion is proportional to the force divided by the mass of the car. This law is expressed by the famous equation F equals to ma, where F is a force, m is the mass of the car, and a is acceleration or change in motion of the car. A larger force causes quicker changes in motion, and a heavier car reacts more slowly to forces. Newton's second law explains why quick cars are powerful and lightweight. The more force and less mass you have, the more acceleration you can get.
Every force on a car by another object, such as the ground, is matched by an equal and opposite force on the object by the car. When you apply the brakes, you cause the tires to push forward against the ground and the ground pushes back. As long as the tires stay on the car, the ground pushes on them slows the car down. In this figure, the black and white pie plate in the center is the CG. This is the weight of the car. LF is the lift force exerted by the ground on the front tire, and LR is the lift force on the rear tire. These lift forces keep the car from falling through the ground to the center of the earth. Magnitude of these forces determine the ability of a tire to stick, and the imbalance between the front and rear lift forces account for understeer and oversteer. The figure only shows forces of the car. Newton's third law requires that these equal and opposite forces exist. If the car was standing still and its weight distribution was 50-50, then LF would be the same as LR. It is always the case that LF plus LR equals to G, the weight of the car. Why? Because of the Newton's first law. The car starts changing its motion in the vertical direction, so the total sum of all forces in the vertical direction must be zero. Braking causes LF to be greater than LR. Consider the front and rear braking forces BF and BR in the diagram. They push backwards on the tire, which pushes on the wheels, which pushes on the suspension parts, which pushes on the rest of the car, slowing it down. The braking forces are indirectly slowing down the car by pushing at the ground level, where the inertia of the car is trying to keep it moving forward as a unit at the CG level. The braking trigger acts in such a way as to put the car up on its nose. Since the car does not actually go up on its nose, we hope, some other forces must be counteracting that tendency by Newton's first law. The only forces that can counteract that tendency are the lift forces, and the only way they can do that is for LF to become greater than LR.